Hello everyone and welcome to this webinar with Tracerco. I'm Callum O'Reilly, Senior Editor of Hydrocarbon Engineering. Now, the title of today's presentation is Optimizing Shutdowns and Turnarounds with Advanced Diagnostics, Insights from Tracerco. Now, as we all know, planned shutdowns and turnarounds are critical for maintenance and upgrades in refining, petrochemical and chemical plants. But they can also be a source of costly downtime and operational uncertainty. Today's webinar will explore how advanced tracer and scanning technologies can transform these events into opportunities for improved efficiency, reliability, and cost savings. We'll start today's session with a presentation on this topic from Andy Burleigh, Senior Technical Advisor at Tracerco. We'll then follow this up with a Q&A session with questions from our audience. So if you do have a question for Andy, you can send this in to us throughout the course of his presentation. For those of you that are joining us on a mobile or a cell phone, you can access the question box by tapping the Q&A icon, which is at the bottom of your screen. And for those of you that are using a desktop or a laptop, just click on the Q&A icon, which is in the top right-hand corner of your screen. You can then click Ask a Question, type your question into the box and click Submit. Now, before we get started, I also want to let you know that everyone who has registered to attend this webinar will be emailed a full recording after today's session. So without any further ado, I'll hand you over to Andy for his presentation.
Thank you very much, Callum. Appreciate the intro. Thanks to each and every one of you out there taking time away from your busy day to join us today. Also want to thank Hydrocarbon Engineering for giving us a platform to get this out to you guys today. Special thanks to Callum and also Marilee in the back who's helped a lot from there to help us get this going. And on the Tracerco side, special thanks to Nicola Porter for helping get everything set up. So with that, we'll go ahead and get started. Today, I'm going to talk to you a little bit about turnarounds and how Tracerco may be able to help turn some of these challenges that turnarounds present into some opportunities to be more efficient. With that being said, here's a presentation agenda, what we'll talk about today. First, we'll start off with some challenges surrounding shutdowns and turnarounds, and then we'll go into the different services that we offer at Tracerco, starting with distillation tower scanning. We'll talk a little bit about true scans, which are scans of trade towers, versus true grid scans, which are scans of packed towers. Talk a little bit about through vision scans, pipe scanning, and phase finder. Those topics down to there are what we call our sealed source services, where we're going to use a small radioactive source, sensitive radiation detector. Everything's going to be kept external to the vessel. Then after that, we'll start talking about some of our unsealed or tracer services, where we'll actually take an isotope or in some cases a chemical and inject them into your process and then trace them through to help you determine any issues that you might be having. We'll talk about flow studies, leak testing, residence time and distribution studies. And then at the end of that, we'll talk a little bit about something that's near and dear to our hearts here at Tracerco. We've increased our efforts to make data more pleasurable, easier for our customers to read, and that is done with our Tracerco Insights platform. And then we'll have a quick conclusion. As I'm going through all these different services, we'll give a brief overview of how the service works, and then we'll give you some case studies that have helped some of our customers in turnaround situations to help them with planning. So at Tracerco, what we do, we've been in business for over 60 years now, and basically what we do is we have a line of services and products that help measure the hard to measure. We use this information to help our customers make better decisions, insight-driven decisions, essentially helping them optimize their processes, saving money, and increasing their profits. Okay, so we at Tracerco work with customers around the world from many different backgrounds. We work for many different types of facilities, from refineries to petrochem, chemical facilities, and then even farther into that, ethanol, LNG, pulp and paper. I'm I'm sure I'm not mentioning them all, but just to give you a brief overview, that's there's pretty much every customer facility type out there that we can touch in some way and help. And over the years, I've been doing this for over 20 years now. And over the years, we've gathered some information from our customers around the world and many different facilities to discuss with them some of their main issues. And one of their main issues is turnarounds. And turnarounds they come in all shapes and sizes. They're not all the same, right? You have some turnarounds that are major turnarounds where you might be shutting down a whole unit, a whole facility or multiple units, down to smaller turnarounds where you may only be shutting down a specific unit or even a small vessel. Planning on these go from years out in advance to unplanned shutdowns, right? So, but in looking at all of that together, there are four main things or main challenges that I kind of want to talk about today surrounding turnarounds. And the first of that is being timing, right? Most turnarounds that we are associated with, one of the biggest issues or biggest concerns they have is, how long is my turnaround going to take? Am I going to be able to do it within the allotted time? Am I going to start on time, right? When do I start my turnaround? Do I push my turnaround back because economic conditions now say that maybe we'd be better served running now and then pushing the turnaround back to when economic conditions might be a little bit different? So total length of it, when to begin, and then the overall deal with timing is you want to minimize the amount of lost production. So when you're down, the facility is not making money, right? And all of these four things kind of intertwine with one another too. The next major topic we would or challenge that people have is usually staying within budget, right? So timing, right, is number one. Budget. I have a budget for a turnaround. How am I going to stay within that budget and not go over? A lot of turnarounds do go over budget. You might have added costs due to unexpected fines when you enter a specific vessel in a turnaround. Wasted man hours whenever you go into a vessel that really didn't need any repairs, but you weren't planning for that ahead of time. If you do go into a vessel and you have those unexpected fines, like mentioned in the first bullet point, now you might increase the time, right? You're going to increase the time that you have to be down because now you have to order ports. Cost of those go up, right? The third would be completing objectives. With every turnaround, there are a set of objectives that are out there that you want to complete. You want to complete all your projects, right? If looking at the first two, timing and staying on budget, sometimes smaller, lower priority objectives won't be able to get done within that turnaround if you want to stay within that same time frame and within that budget. And then finally, safety. Safety is a big issue for these turnarounds. A lot of times you've got people that aren't accustomed to being in the plant there. You've got people working around the clock. You've got shifts around the clock, a lot of activity. And with that, we always see that a lot of safety issues, be it small safety issues to injuries, even to some, to the extreme case, deaths, occur during turnarounds. So at Tracerco, we do offer some solutions to help you optimize these turnarounds, help you with your planning. From a timing standpoint, we can offer some services that help you determine whether or not you need to go into a vessel, right? If you know that ahead of time, you can eliminate that unneeded vessel entry, and then that would allow you to either shorten the time of your turnaround, or we can take the same amount of time and do some of the other stuff, like complete some of those other objectives that you might want to do. Help you stay within budget. To help you stay within budget, if you know ahead of time how many ports you might need within a specific vessel, you can order them out ahead of time. Again, saving time once you get in, and then saving cost on those actual pieces of equipment that you might need. Completing objectives, we kind of talked about that in the timing side of it. If you have more time, because you've eliminated some vessel entries, you've saved some time from knowing exactly what parts you need, you have a lot of, you're well planned, then you can actually be, potentially complete all of the objectives, even the smaller ones. And then from a safety standpoint, if we by what we talked about before, reducing unnecessary vessel entries, you're again reducing the overall length of time. Specifically with entries pose a lot of hazards. So if you can reduce that, of course, you're going to be more safe, reducing the overall length of the outage would also increase your safety because you have fewer people there for for a longer period of time. So with that being said, I'm going to start going into some of the services that we offer, and we'll start off with our tower scanning services. So what is a tower scan? A tower scan is basically a inspection of the vessel while it's online and running. For trade towers, we offer our true scans, where we do a single scan, typically through the active area of a tray. What can these scans tell you? Well, one of the things that they can see, and one of the things we're most often looking for, is mechanical integrity. We can tell you by doing these scans if your trays are in place, right? Or that you have any damage. We can also detect process degrading conditions such as flooding, foaming, weeping, entrainment, things like this, okay? Why do we do scans? A lot of scans are done for a troubleshooting case. We're having an issue with the column, but we do a lot of scans for pre-turnaround, and that's kind of what we're going to focus on today, to help people plan, right? So to alleviate those issues that we were talking about previously. So here's an actual scan. We have a small radioactive source, sensitive radiation detector. We lower them down opposite sides of the vessel. For trade towers, we typically scan through the active areas. So we align the source and detector to where they run parallel to the downcomers. That being said, we do have the capability of scanning downcomers as well. Sometimes we can move over there, especially in a flooding scenario, and you want to determine whether or not my flood is initiated on my tray deck or it's initiated in the downcomer. We'll slide over and scan downcomers as well. We also, if you have multiple pass trays, multiple pass active areas, sometimes we'll do multiple scans on different active areas, especially if you look expecting damage on one side versus the other. Okay, so this is the type of output that you get from a gamma scan. We have a graph here. On our y-axis or vertical axis, we have elevation. On our horizontal axis or x-axis, we have radiation intensity or density. I won't go deep into the science behind this, but basically there are a few different constants, a few different variables that could affect how much radiation that detector sees. Time is one of them, and that's constant. We take the same length count at every spot we check on the vessel. Second is the distance between the source and detector, and which that pretty much stays consistent from top to bottom, as well as we lower them right down the edges of the vessel. And then the third thing is the density. So, and that's actually changing. So that's the one thing that's not constant. So what we're getting here is a density profile. Okay. So basically, if you start at the top, and I didn't mention, I'm sorry, on the x-axis, stuff on the left-hand side of the plot is more dense material. Right-hand side of the plot, less dense material. Liquid side versus vapor side. Okay. So we start scanning, and basically the way this works is all of our equipment is gravity fed. So we zero our source and detector at the top tangent line. We take a reading there, drop it 2 inches, take another reading, drop it 2 inches, take another reading, so on and so forth till you get to the bottom of the tower. And this is the output you get here. We're looking at, you should see clear vapor at the top, which we do. And we get a little absorption for this reflux nozzle here. And then we start to attenuate, the signal starts to attenuate when we hit the froth on top of the top tray. And then right beneath that, it snaps back to the right, okay? And that's what you like to see. The reason we scan parallel to that downcomers and not through them is because you want to see if you have good liquid vapor disengagement underneath each tray, which would be shown by the scan snapping back to the right. When we look at these scans, there's a few different things we look at. We look at the span of each tray, point from lowest density to highest density. We'd like to see that pretty consistent from top to bottom. If some trays show up less dense, that could mean things like damage. If they show up more dense, it could tell you like you might have some flooding or fouling going on. We also look at the shape of this curve and how far it comes back to the right. That can help determine the difference between weeping or entrainment, okay, and then the severity of it. And then we also measure the froth on each one of these trays to see how much tray space you're actually using and how much you have available to you. So here's an example of a column that was scanned ahead of a turnaround, and you can see we kind of cheated for you here, right? We gave you a good red rectangular box here that shows the area of concern. These trays up top look pretty good, pretty consistent density from the top down to, say, tray 12 and then tray 13, I'm sorry, and then at tray 12 it shows up a little bit less dense, holding a little bit less liquid, and you can see it really gets bad in this area right here. The scans aren't going out as far to the left, and they're holding a lot less liquid. This is indicative of, this is what tray damage would look like. So heading into a turnaround, this customer knows, before they even, think about entering the column, hey, I need to have at least enough tray parts in order to replace at least 12 trays within this column, okay? Here's another potential, we're gonna talk about a process degrading condition, in this case, foaming. This customer called us and they were having differential pressure issues. When they ran at full rates, getting liquid carryover, not operating well at all. So we came in and we did an initial scan, and this is actually at lower rates, so they're not running the rates they want to. And we were able to tell them that it was foaming. Foaming has a very unique characteristic on a gamma scan. You almost get the stair step effect on the top of the trays. So in this case, we were able to tell them, hey, you're foaming. They weren't seeing issues at this rate, so they went ahead and raised their rate. Went ahead and raised their rate, and we did a second scan. And you can see this red scan line right here, the foaming gets a little bit worse, and it gets to the point where they start backing up liquid and flooding all the way up to the top of the tower. In this case, they had the capability of adding some anti-foam. We did a scan after they added anti-foam with the higher rates, and you can see everything pretty much cleared up. I know it gets a little cloudy there because we're looking at 3 different scan cords, but take my word, the green scan line, everything looks pretty good. You can see the floodings out of the tower. They are heavily loaded, but you're still not, you're still making good product, and you still have a little bit of room to go. So this is one of those cases where, opposed to, not doing a scan and shutting down and going in to look at this vessel, they would not have seen this issue because this is a process-related condition. So by us being able to do the scan while they're online and running, we're able to diagnose that so they could handle it the way they wanted to. You could, without actually going into the vessel. And then also with the amount of anti-foam they were using, we could actually do additional scans to help optimize that as well. So trade towers and pack towers, we look for many of the same things. We look for damage that we talked about, the process degrading conditions. But with pack towers, instead of one additional thing that is important is whether or not you have good distribution through the packing. So in what we employ for pack tower scans is what we call a grid scan. This allows us to see some distribution qualities. So instead of doing a single scan from top to bottom, we do 4 scan lines. Don't bring out 4 sources and 4 detectors. It's 1 source, 1 detector. We measure out each one of these scan cords to be the same length. And then we start at the top, scan one of the scan cords, pull our source and detector back up, realign, do the second, do the third, and do the fourth. And then we take all this data and we overlay it on the same plot. So if you have good distribution, you should expect to see a similar density where all 4 of the scan cords overlay well with one another, where you're not seeing that here. The red showing up a lot more dense. We also look for consistent density from top to bottom of the pack bed. Here's an example of a tower that we scanned. We have both a baseline scan and a pre-turnaround scan, right? We didn't talk a whole lot about baseline scans up until this point, but baseline scans are done following a turnaround when the column is known to be clean and operating well. We'll talk a little bit about them here and a little bit farther down the road, but it gives you a good idea for comparison purposes. So you can see here on the baseline scan, everything was pretty good through the pack beds. Distributors look evenly loaded. Pack beds, consistent density from top to bottom, overlaying, intermingling amongst the 4 scan cords, showing good distribution. We actually see an increase in density here, the bottom of this bed too. That is due to a different type of packing down there, and then everything looks good throughout. Here's the same tower pre-turnaround scan. You can see the spread amongst the 4 scan cords, very bad distribution, liquid hold up actually into the distributor up top. And in the top bed also looked very bad with some fouling and some liquid holdup. So by having this type of information, customers are able to determine what kind of repairs might be needed when they shut down. Here's another example of one where we have some damaged packing. We were called out to do this scan after an upset. A customer had an upset, started making off-spec product. They came in, had us come in and do a scan, and this is the results right here. So we started up top. Everything looks pretty good through the demister. All 4 scan cords overlay pretty well with one another. Coming on down, and then here we see our first problem. When we get to this distributor, we're seeing about 24 inches of dense material where we should only be seeing about 6. So something's definitely going on here. keep scanning down where this crosshatch section starts right here. We should be starting to see packing, but we don't see any until we get a couple of feet down from there. All four of the scan cords are not intermingling well with one another. So bad distribution. And when you get down to the bottom, you actually see only one of the scan cords kicks back to the right like they all should. So what had happened in this case is they had a pressure surge to the column, knocked out the hold down grids. This was random packing, actually blew some of the packing up into the distributor, causing the liquid back up there. And then you can see some of the bed was collapsed as well. So this is very important information going into the turnaround for them, because one, they knew, hey, we can't keep running right now. We're not going to be able to make the product. We need to go ahead and schedule an outage. And then they know what they need to do when the outage occurs. They need to have some packing. They need to be ready to clean out that distributor, and also look potentially at the distributor to see if there were any damage there from the pressure surge as well. Here's another. This was actually, we did grid scans on this, but I'm only showing a single of each. The red scan cord actually is done when the tower was dry, before it started up, just to measure what kind of density levels we were seeing through the packed beds. Everything was good. This is as soon as they start up, they're off-spec product, high differential pressure. So they call us to come out and do a scan, and the blue scan line represents that. So what we have going on here is basically from the time we started scanning, we're getting a lot of dense material. They've got liquid all the way out the top of the vessel. You can see through there, through the distributor, all the way through the top bed until we get to the redistributor above the top bed. What had happened in this case, and then you can even see the bottom bed is pretty much the same density as it was when it was dry, so you're not getting hardly any liquid down there. What had happened in this case is the redistributor, when they were putting it into the vessel, they left it came in on basically a piece of plywood. They left the plywood in as well, so no liquid could flow through. So this was an immediate re-shut down, and but at least they knew where to go. They knew they had to look at that redistributor. They pretty quickly were able to pull that out, button it back up, and everything started working well after that. So what I've got here is an example of, for one facility, we scanned, this was a pre-turnaround scan package. We did 19 different vessels. I know it's a bit wordy. I apologize for that. And you don't have to focus on too much of reading the whole thing, but I will let you know that there's 19 different vessels that we scanned within 6 different units within this refinery. We have them color coded. Anything in red means there was a mechanical issue found with that vessel. So with 4 of the towers, there were mechanical issues found. So this allowed the customer to order the parts that they needed ahead of time and help them plan for how they were going to approach that during the turnaround. Of the ones listed in blue, process problems were detected. Some of those process problems might not even need an entry to fix. So by knowing this information ahead of time, customers were able to determine, hey, do we actually need to go into this vessel or not? And then the big one is 12 of the towers, or 11, one of the towers had a couple of parts of damage, but the rest of it was okay. So 11 full towers, and then a partial another one, had no issues whatsoever. So if it wasn't at a time whenever they were required to go in and enter this column and stay within regulations, they could mark those, remove those from the turnaround list, saving them a ton of time. We talked a little bit about baseline scans a moment ago. Baseline scans are scans that are performed after a turnaround, when the column is when you start back up and the process is clean. The column is known to be clean and operating well. They serve as a very good use for comparison purposes moving forward, but they also help to determine that you had a good startup. Remember the packed tower we looked at just a second ago, where they had the piece of plywood underneath that redistributor. That was a case there. Sometimes we see stuff damage at startup. So we've also found, for a lot of our customers, sometimes it's difficult to say, hey, we're going to spend more money on scans when we just went through a turnaround. If you put this budget for the baseline scans into the turnaround budget, then the money's already there. So for packed towers, we talked about grid scans, and that's still the best method for looking from top to bottom of a packed tower. But if you think about the 4 grid scan lines, the percentage of the cross-sectional area that they cover is pretty small. Very good tool for seeing quartile maldistribution where you have more liquid flowing down one side or the other. But what happens if you have something that's equally maldistributed, where all your liquid may be flowing right down the middle, or all your liquid might be flowing down your edges of your vessel? The grid scan wouldn't necessarily pick that up. However, we do have our through vision scans, same type of source we're going to scan the tower with, same detector. And we're going to show it's going through a little animation here. We had the source on one spot. We take 9 different detector placements around in a fan beam pattern. Then we move our source to another location, do the same thing, so on and so forth. So instead of only the 4 data points, now you're looking at 81 data points. Now, it's one elevation, and we do need 360-degree access to do these, but this is the type of output that you get. And it is able to see that equally maldistributed liquid that the grid scan might not necessarily pick up. And these aren't just done on packed towers. They can be done on reactors and risers, piping, anywhere you needed a detailed analysis. So here's a case study where this is right after turnaround. Customer started up a baseline type of scan, but they were having issues. They were actually making off-spec products. So they had us come in and do a grid scan of the vessel. And this is the grid scan results here on the right. Everything looks pretty good. Everything's pretty evenly loaded. Good overlap between the 4 scan cords through the packed bed, consistent density from top to bottom. There are a couple of spots here where you had a ring and you had a platform here, but other than that, consistent density from top to bottom of the packed bed. Since they were still making off-spec products, they decided to go ahead and do a through vision scan right near the top of the packed bed below the distributor. And here are the results. Each one of these colors represents a different density range. So if you had good distribution, you would expect a consistent color throughout the whole vessel. In this case, you see these 2 blue sections here, deep blue sections. If you look down at the scale, that's 8.5 to 9 pounds per cubic foot. That's actually the dry density, bulk density of this packing. So essentially what's happening here is they have 2 large dry areas within the packed bed. I've gone ahead and overlaid the orientation of the trough and lateral distributor. And you can see basically what's happening is they're not getting any liquids out to the laterals in this case. We didn't have these orientation drawings available to us when we did the initial scan. So we did the typical north, south, east, west scan cords. If you look closely, each one of those 4 scan cords intersects the same amount of low density material in this case. So when you put them on the plot, they actually look like they're a similar density. But the through vision scan was able to see that in this case. In this case, what had actually happened is they had redesigned that distributor coming into the turnaround, and what they didn't take into account is this new distributor needed more liquid force, more liquid head to get the liquid out to the laterals. So they kept that same distributor in there, but they actually did a piping revamp to get more liquid head to it, and then the column worked fine after that. But this was the information that was needed to help determine that. Next, we'll talk about pipe scanning and phase finder. We see quite a few instances where plug pipes cause outages, right? Or you have a plug pipe and you need to go in. We have a couple of different methods that we use to scan pipes. One, our phase finder that would work some differences in hydrogen content. And that's the first example we'll show here. We're coming by, and it can actually see that you have different phases within or different materials within that piping. And a lot of times that's all people want to know. They just want to know, where's my issue, so I know where I can go in, cut it out, heat it up, whatever I got to do to get rid of it. In other cases, folks might want to know exactly how much buildup they have, and we can use our gamma scan technology. As long as you know the density of this material here, we can tell you the exact depth of buildup that you might have. And then to go even a step further, some folks would like to know exactly what the shape of this buildup looks like, and then you can do the through vision scan. You can see there it comes there. So here's an example of a flare system where we use pipe scanning, and phase finder to tell them a bunch of different things. We're able to see in this drum, you measure where the liquid level was, no hydrogenous material above it, right? So the walls look clean. We're able to verify that this internal baffle was in place by measuring levels on both sides of it. And then we also were able to measure the amount of buildup they had in this system, so they know exactly where they need to go in and remove it. Just very useful information when you're going into an outage to know exactly how much you can expect and and where it's at, so you can make the best decisions of how you're going to remove that material. For the phase finder, we'll talk a little bit more in detail about it now. You saw what we were using for the pipe scans there, but what this is the scans that we talked about to this point, we were using gamma sources. For the phase finder, we actually use a neutron emitting source. You can see it slide down the vessel there. Now our source and detector are both on the same side. The way this works is fast moving neutrons are shot into a medium, and then slow moving neutrons that are reflected back are picked up by our detectors. Roughly a hydrogen atom and a neutron are about the same size. So the more hydrogen you have within the material we're shooting into, the more reflection you get. The fast moving neutrons penetrate pretty far. The slow moving neutrons may only be able to travel through about 12 inches of material. So we're not seeing all the way through the vessel, but you can see stuff that's happening within 6 to 8 inches of the vessel wall. Very good tool for inventory purposes when you have multiple phases within one vessel and you wanted to measure them out like we have here, where you have an oil phase, an emulsion, so much water. It can also see solids built up within the vessel too. So we get a lot of calls where we come in, one for inventory, two, people want to know how much solids they have in the bottom of a tank so they know how many vacuum trucks or whatever means of removal they might need to get that out, so they know how much they need ahead of time for planning purposes. Like I said, we can't see, it doesn't see all the way through the vessel, so we don't know necessarily what's going on in the middle, but we can take readings around the circumference of the vessel and map out at least map out your solids level along the wall so you have a better idea. This can also be used in helping to measure levels, and we find it quite often people run high bottoms levels, especially within their towers. They don't realize it. Maybe their level measurements off calibration, whatever the case may be. It's pretty quick. We can do it with the scan too, but it's pretty quick to come out with the neutron backscatter device and say, okay, here's your liquid level. What is your instrument reading? And we can help you guys calibrate that and help solve those problems for you there. Because when you run that bottoms level up over your vapor inlet, we see a lot of stuff get damaged quite often. So being able to help you, one, tell you exactly where your level's at and help calibrate your level instrumentation could be quite beneficial. So that's the sealed source services that we have to offer. I'm about to start talking about some of our tracer services or unsealed source services. For these, we are either going to take a small radioactive source, and when we use radioactive tracers, we use short half-life isotopes, okay, just to let you know that so they're not hanging around for a long time. Either that, or we're going to take a chemical and we're going to inject them into your process. And then we're going to follow them around to tell you different things, like we can see flows, leaks, distribution, residence times, and we'll kind of talk about that in a minute. Before I get started, I want you to know we have a vast library of these tracer materials to choose from. We have liquid phase, we have gas phase, we can even tag solids, we have aqueous, we have organics, we have materials with different boiling points. Basically, we have a tracer that will mimic anything you got out there in any of your processes, okay? So the first we'll talk about are flow studies. It's probably the simplest of the tracer studies that we perform. And what we're going to do is we're going to take well, first, why do we do them? One, to verify flow meters. Quite often, a lot of times we find people may trust flow meters at high rates or low rates, but not necessarily at the other. And then we also use them to look for things like leaking valves, fugitive flow. But the way the test works, you just saw it go through. We'll inject a pulse of radiation into the pipe. We'll set detectors up at known distances apart, and then we measure time of flight from point A to point B. Sometimes we use multiple detectors, more than two. By knowing that, you have a velocity, and then by knowing pipe diameters, pressures, temps, whatnot, you can actually calculate a volumetric flow rate. Like I said, we're verifying flow meters a lot. A lot of times, customers will actually have their flow meter reps come out while we're doing the testing to help calibrate, so they now trust them at high and low flow rates in some cases. This case study I'm going to show you regarding flow rates is around a flare system. In this case, we had a customer that came to us, more flow to the flare than they would expect, and they weren't sure where it was coming from. So we were able to do a test where we'll inject a pulse into the main flare header, set up detectors at known distances apart, and look for an increase in velocity. In this case, we saw an increase in velocity after unit 2. So unit 2 was the culprit. Had there been another one leaking, we would have seen another step change increase in velocity, and we could have tested that unit as well. But in this case, it was just one of the units. We're able to go back into the unit, do another test in the unit header, injection into the unit header, set up detectors after each of those potential leaking entries into that header, and determine that they actually had leaking PSV. All right, so that was causing the whole issue. So imagine how much time this could save you instead of shutting down or sending people out into the unit to try to pinpoint exactly what may be leaking. This is a pretty quick test, able to tell them exactly where they need to go, what needs to be fixed, instead of shutting the whole unit down or shutting multiple units down to go look for it. We can also use this flow studies to determine if you've got balanced flow, where you might, in this case, we have two different lines going to fans, comes in a common line. If you think you might have more flow to one side versus the other, you can do this type of testing. Maybe it's 3 or 4 lines, whatever the case may be. Maybe you have some pluggage causing, directing flow somewhere else. This is another use for the flow measurements. Probably the most popular of the tracer studies that we perform are our leak testing. Leak testing services that we perform mostly on heat exchangers, not only, but a lot of times on heat exchangers. So why do we do them? Typically, a lot of times our customers know that they might have a leak, but they're not sure which exact exchanger might be leaking. Maybe they have several exchangers in a bank of exchangers, or maybe it could be an exchanger leak or something else is going on with the process, like maybe bad catalyst or something like that. So we can come in and do a leak test for them to confirm, or either confirm it is an exchanger leak or say no, it's not, right? So I'm going to show you a couple of different methods that we would use. The first method, we're going to inject a small amount of radioactive material into the high pressure side of the detector, and we're going to set up, high pressure side of the exchanger, my apologies, and we'll set up detectors on the low pressure outlet, okay? If you have any crossover of that isotope from the high pressure to the low pressure side, then the detector, in this case the blue one, on the leak side would get a response. And now we're looking at, on this plot, tracer intensity versus time. So if it occurs at the right time and we get an absorption, that means that, or a response, that means that that exchanger is actually leaking. Then we can measure the area under each of these curves to actually determine the size of the leak. This method can see leaks down to 0.5%. That's 0.5% of your total flow coming into your high pressure side of your exchanger. And results are given the day of the testing, okay? Here's a real-time example where a customer approached us. They had pretty much gotten it down to, we have a leak, but we don't know which of these two exchangers could be leaking. We want to know which one it is, so whenever we do shut down, we don't have to go into both of them. Or if both of them are leaking, we could, we do need to go on both of them, but they wanted to confirm that. So what was done, the high pressure side was the shell side. Here we did an injection there. We set up the detector to watch it go in. And then we also have a detector here to watch it go between the two shell sides. These are two in series between 1A and 1B. And then we have your outlet here. So that's where the tracer should flow with no leaks. We have a leak detector here set up. If B was leaking, it would come back through and we'd see it here on the tube side. And we also have verification leaks detectors for A, and then also to confirm if we had a leak on B, it would show up here too. So we always just kind of we always want to have an extra, not just one leak spot. We'll usually set up 2 or 3. So you can see here's the results. Saw the tracer go in, and we're looking for any response on this green and pink or purple detectors. Very shortly after the isotope entered, we saw an increased signal on the green and pink detectors up here, which means, we got a leak. And it was before it even entered the B exchanger, so we knew it was A. And then if you look down here, the leak detection for the B, no response was seen. So in this case, we're able to tell them with certainty that E1A was a leaking exchanger. So whenever they did decide to go ahead and shut it down, they knew exactly what they needed to go into, which one they needed to go into. Sometimes now, especially with ultra low sulfur units and whatnot, smaller leaks can pose a problem, right? A bigger problem. So we've had to come up with another method to see smaller leaks. And the way we do this is we inject a chemical now into your high pressure side. Instead of setting up detectors, we actually pull samples on the low pressure outlet. These samples are taken off, sent to lab for analysis, and then we can see a smaller leak probably as you need to see. The smallest we've had to go after is a couple parts per million, but these tracers can actually be picked up in the parts per billion or even parts per trillion range in some cases in the lab. So can find very small leaks. The one downside is that this does take a few days to get results back because of the analysis part where we have to send samples to the lab for analysis. So it might not get results for a couple of days. Here's an example where in a C2 splitter system, we had an inner boiler or a reboiler, and they were pretty sure that one of them was leaking into the propylene system, but they weren't sure which one it was. In this case, we did 2 injections, one into the inner boiler, and we pulled samples on that propylene system, and the same on the reboiler, and pulled samples off of that. And here are the results. What was able to be determined is that the inner boiler was actually the leaker, so they knew where they needed to go in and make repairs following this data. Residence time and distribution studies, excuse me, kind of combine them together. Residence time studies are often done whenever you think you might have short circuiting in the system, excuse me. Short circuiting in the system, you might have some sludge or something build up within a vessel, causing it to short circuit, whatever. It's very similar to a flow study, except for you put a vessel in between. So you put an inlet detector, outlet detector, and measure how long the source takes to get through the vessel. And then oftentimes when we're doing these, we also combine it with a distribution study. So we can set up rings of detectors around the circumference of a vessel and measure what the flow looks like as it's going through. Here's an example of, another simulation. So we'll put an inlet detector, outlet detector down here. We have rings of 4. You can use more than 4 too. It just depends on the diameter, size of your vessel, and how much detail you want. If you get good distribution, you should get a similar response on all the detectors around the circumference, as opposed to what poor distribution might look like here in this second. You have your inlet, your outlet, so you measure your resonance time throughout. This is very important. I mean, distribution quality through some reactors, will determine whether or not they do what they're supposed to do or not. So having this information ahead of time, ahead of a turnaround, can help you determine what kind of changes you may need to make. As you can see in this case study here, in an FCC unit, one of the issues they were finding salt and pepper regenerated catalyst, which meant they were having incomplete combustion, and they were suspicious that the air grid the distribution from the air might be bad, because of the air grid. So they needed confirmation. They called us in to do a test. We inject into the gas system. We set a ring of detectors up above the air grid. We just did 4, 1 north, east, south, and west, and here are the results from that. So if you measure the area under each one of these curves, it tells you the percentage of flow that you had to each side. The blue one, or the west side, was getting much less flow than the other 3 sides. So they did confirm that they did in fact have an issue with their air grid. So whenever they shut down to go and fix this problem, they knew exactly where they needed to go. They need to go fix that air grid in the bottom. So I've been doing this for quite a while. And I remember the days when I first started where we would go and scan a tower or do a tracer study. And then we'd spend a lot of time printing stuff out, and we'd bring it to the engineer to go over results and have a long piece of paper that we'd have to look at. And then we've kind of evolved to going electronic from that point. But what we've done here at Tracerco is we put a lot of emphasis in the recent years on giving our customer better access to their data, making it a better presentation for them. And that here comes our Tracerco Insights platform. So not only are we trying to better the customer's ability to look at our data, we've actually set this Insights platform up for customers where this is a cloud-based system, and we can actually put all of your information for your specific facility in this site. So now you can have all of your engineers have access to it, and it works as a database, right? You can it's pretty easy, it's user-friendly, easy to log into. It's very secure site too. And basically what happens is we'll put all of your reports here in the portal. They now live in the portal. We actually have interactive portions of it as well with our tower scans, where you can actually go in, zoom in and out on the towers. You actually have the tools available to you that our field engineers do when they're actually working up your data. So now you know where your data's at. You can look from historical purposes. Hey, have we scanned this vessel before? You can look in there. Of course, you can always call us and we can look it up. We have it in our database as well, but now you have it at your fingertips. What if you have multiple scans on the same vessel where you monitor time, over time, where you do scans every year, annually, 6 months, whatever the case may be. If you have historical data on there, you can actually turn scan lines off, turn scan lines back on to see and compare what it looked like previously to what it looks like now. Very useful tool, and it's all at your fingertips now. So again, thanks for joining. As a quick conclusion, I know we talked a lot about a lot of different things today, but overall, shutdowns and turnarounds do prevent many challenges to our customers, but they are necessary. Facilities need to do them to, one, stay in regulatory compliance. You need maintenance work to extend life of equipment. You need to repair equipment, and basically to help optimize your performance. With the services we've covered here today, hopefully I gave you some ideas of how Tracerco can help ease the burden of these challenges and maybe even turn them into opportunities, helping you minimize downtime, improve decision-making and confidence that you have in those, help ensure a much safer and much more efficient return to operation. And with that, I want to thank you all again for your time today. Thanks for taking all the time out of your busy days to join us, and I'd like to open the floor to any questions.
Great, Andy, thank you so much. That was a really interesting and very detailed presentation. I think you've really clearly demonstrated how advanced diagnostics can help to transform shutdown and turnaround events. And it's always really nice and fascinating to see some real case studies and examples of this in action within facilities. Really good to get a clear idea. So great stuff, Andy. Thank you very much.
Thank you, Callum.
As you mentioned, we're now going to move on to the Q&A section of today's webinar, and I can see we've had quite a few questions in already, which is great. If you do have any further questions for Andy, now is your time to submit them to us. As a quick reminder, if you're using a mobile or a cell phone, you can access the question box by tapping the icon at the bottom of your screen. And if you're using a desktop or a laptop, you can click on the Q&A icon, which is up in the top right-hand corner of your screen. You will then get a box that asks you to ask your question, and you can type your question into the box and click submit. Okay, Andy, let's try and get through as many as we can in the time that we've got available to us then. So first up today, are there any size limitations for vessels in regard to scanning them?
Oh, excellent. That's an excellent question. Thanks. We kind of pressed for time, so I didn't get to cover that exactly. But to answer your question, not directly, but the short answer is yes, there are limitations to the size. Things with very large diameter, also limitations with thickness of walls that we're shooting through or density of the material that we are potentially scanning through can all affect if we're able to get enough radiation through when we're talking about scanning. Now, that being said, we are able to scan vessels up to, 30 feet plus in diameter, down to piping, with 1 inch to 2 inches in diameter. From a thickness standpoint, we are able to scan some vessels with walls greater than 6 inches thick. But if you combine the two with a large diameter and very thick walls, sometimes it becomes very difficult to scan. But to answer, the best way to handle this is if you have something specific in mind that you're looking to scan and you're worried about size limitations, just let us know. And if you give us those dimensions, the diameter, the wall thickness, and the density of the material we're shooting through, we can pretty quickly do a calculation for you and let you determine, are we going to be able to scan it or are we going to have to look for something else? Excellent question. Thanks.
Great. Thanks, Andy. We actually had another question came in that it was very similar to that, asking about what the smallest pipe diameter for detection of deposits were. I think you've just answered that. Did you have anything else to add to that?
No, but I'm glad they came up with that because, yes, typically we scan down to 2-inch pipes comfortably. There are some occasions where we can go a little bit smaller than that, and it depends what you're looking for. So if you let us know some specifics, is it insulated, not stuff like that, we might be able to get even smaller than 2 inches. So
Great.
Thanks.
All right. Lovely, Andy. Thank you very much. So we have another question here that's asking if you can talk to any recent developments and uses of tracer technology in hydrotreating reactors specifically.
Yeah, I mean, I don't have any specific examples to show you, but yeah, I mean, we're doing tracer techniques and hydrotreaters quite often. It just kind of depends what kind of issues you're having. Are you looking for leaks? Are you looking for distribution? Some of those, and also, you know, the size limitations will come into effect there. So yes, we do a lot in hydrotreaters. I have to have some more specific and some more specific information to determine exactly if we can help you with your specific hydrotreater. But again, it's one of those things. If you let us know sizes and what kind of issues you're having, we would be happy to let you know what type of services we have available to it.
Great, thanks, Andy. And another question here is, in the phase finder example that you presented earlier, do you make the measurements around the vessel on the periphery? So let's say for liquid at the bottom of the column or solids at the bottom of the tank.
Yes. When you say around the periphery, I'm assuming you're talking about around the circumference. That is what we do. So we'll shoot from top to bottom in one line, and then we can move around the periphery or the circumference of the vessel and take more readings around, so you have a better idea what's happening around the walls all the way around the vessel. Good question.
Thank you, Andy. Another one here is asking if it's necessary for insulation to be removed from vessels in order to perform your services.
No, good question. In most cases, and the short answer is in most cases it's no. Typically on tower scans, they don't need to be removed unless they're in the way. Like if sometimes you have insulation that gets butted up against behind a toe board of a platform or something like that, sometimes we need to move it around a little bit. But for the actual scan data itself, not typically. Sometimes when we're talking about pipe scans on a smaller diameter, especially if you have a smaller diameter pipe and you have a thick amount of insulation around it, sometimes it helps to remove it, but it depends on exactly what you're looking for. It's kind of a case-by-case thing. But I would say in general, most cases it's no.
Great, okay. And another question here is asking, how far ahead of a turnaround or outage do most clients begin utilizing your services for the planning stage?
That's a great question, and it's not a single answer, right? It kind of depends on how they're planning, what type of turnaround is it? Is it a major where they're planning out years in advance, or is it a shutdown that's going to happen in the next couple of months, right? So typically on the larger, when you have more time to plan, typically they start scanning anywhere from 18 months out to about 6 months out, depending on their philosophy. Sometimes they'll scan 18 months out and then something happens and they might scan again as they get closer. And then others, they start scanning, as close to a couple of weeks ahead of the outage. So, but that is a really good question. So it kind of depends on your philosophy. The farther in advance you do it, the more time you have to plan. So.
Great, thanks, Andy. So we've got time for maybe 2 or 3 more questions. So if you do have a question for Andy, this is your final call to get it into us, and we'll try and get through as many as we can. So please use the Q&A tab and send it in, and we'll try and get through as many as we can, as I mentioned. Okay, Andy, another question we have here is asking, can you spot a partially stuck disc of a butterfly valve in a large diameter water service?
Possibly. We'd have to look. Again, this is going to determine on the thickness of the disc and what kind of access. And I didn't mention earlier, when we're doing pipe scans, we do need to be able to get our hands on it. So what kind of access we have. We need some good drawings. If the disc is thick enough compared to the diameter of the pipe, we might be able to see it potentially with a gamma scan. Another thing that you might be able to do is you might be able to see the effect of it, like with a flow rate or something like that. So it's on a case-by-case basis. We'd have to look at some drawings, but yeah, there's definitely something we could potentially do to help you figure that out.
Great, thanks, Andy. And another one here is asking, how soon after startup do you typically perform baseline services?
Good, another good question. Again, as soon as you can. You do want to be up to rate, right? You don't want to just start up and kind of limping along. So typically they're done within the first couple of weeks of starting operation, assuming that you're up to full rates. Sometimes they'll wait a little bit longer if it takes them a little while to get up to rates. Sometimes it's as soon as, the day after if they start at full rates. But you want to do it as quick as soon as you can after you start up, so so no other problems evolve. That you're no longer doing a baseline and now it's a troubleshooting scan, right?
And as a follow-up to that one, we've had a question asking what time is typically required for a baseline scan of a column or a reactor? Are we talking hours, days, weeks?
Excellent. As far as the time for the scan itself, it's going to depend on the size of the vessel. Most towers, and to put it in the perspective of the way they ask the question, it's hours. It's not days or weeks. Most scans take from anywhere from an hour to a day or so to complete the data. Larger towers, of course, take longer time to scan. Same thing with reactors. When we start talking about the tracer studies that we're doing, those tend to last a couple of days. We usually have a day of setup. I told you that we use short half-life isotopes, so we usually have a day of setup ahead of time, depending on how many detectors we need. And then, so everything's ready to go. And then the short half-life isotope we get in, it doesn't live for a long time. So when we get it produced and brought to site, that's usually done on the second day. So depending on how many days of setup, that might take days. So for scans, it's usually in the hours time frame. For some of the tracer studies we do, it's hours to days.
Great, thank you, Andy. Maybe one more question that we've had here is asking, can you also scan rectangular ducts, or do you specialize in vessels and pipes?
Could you repeat, Colin?
Yeah, sure. So is it possible to scan rectangular ducts, or would you specialize in round vessels and pipes?
Oh, for sure. Yeah, that's a good question. Like rectangular ducts, yes, we can scan rectangular ducts. My apologies. And as long as the geometry is right, yeah, absolutely. There are some cases where we scan rectangular stuff. Absolutely.
Great, thanks, Andy. So I think we're coming towards the end now. I was just wondering if you have any closing thoughts or comments for our viewers today.
Oh yeah, thanks a lot. Again, thanks to everybody for taking time out of their busy day to join us. Hopefully, I didn't put you to sleep, and you learned a little bit about how Tracerco can help you turn your challenges from a turnaround into opportunities to improve them. And again, thanks to Callum, Marilee, and to Nicola from the Tracerco side as well for all the help with putting this together. Appreciate it. If you need anything, feel free to reach out. If I can't get an answer to you, I'll get you in touch with the right person who can. Thank you again.
Great, thanks, Andy. Like I say, I just want to thank you again for a really interesting presentation and for taking the time to answer our audience questions. Apologies to our audience if we didn't get around to your question this time, but we do have a copy of everything on file, and we'll make sure that they're passed on to the team at Tracerco. I'm sure we'll be happy to get back to you. Also, Andy's contact details are on your screen now, so jot them down. If you do have any further questions for Andy, I'm sure he'd be happy for you to, as he mentioned, shoot him a line, and he'll get back to you, or one of the team will, as soon as possible.
Absolutely.
Before we finish, a final reminder that everyone who has signed up to attend this webinar will receive a copy of the presentation via email shortly. So keep an eye on your inbox, and that will be turning up there. And that's a wrap for today. So Andy, once again, thanks so much for your time today. Really appreciate it. And thank you to everyone for joining us.
Thank you.